Okay, so we are just continuing where we stopped. So that was the blue part. Now I'm going to draw the, let's do red. If I use the right-hand points, you see that I am overshooting the area. So area using the right points will be f computed at 2 dx plus f computed at 3 dx plus f computed at 4 dx delta x, which is approximately, actually, I should have put approximate here. That was a bad spot for approximation. There we go. So this is equal to square root of 2 times 1 plus square root of 3 times 1 plus square root of 4 times 1, which approximately is 1.4 plus 1.7 plus 2, which is about 5.1. So now with these two calculations, I learned that the actual area is in between these two values, 4.1 and 5.1. Now you can go and average those numbers. You still won't have it exact, but you know, it's somewhere around 4.6, let's say. Now we can check that luckily because we know how to compute this integral. So that's x to a half, right, square root, which is x to the 3 halves divided by 3 halves from 1 to 4. So plug in 4, square root is 2, 8, so 16 thirds minus 2 thirds, which is 14 thirds. 3 into 14 goes 4 times, that's 12, then 20 is 0.6. And then 6 times 18, that was 20, so it's 2, so it's 0.666. Yeah, I'll just put 666. There we go. So, yeah. So you see that we were able to get close to the actual area. Now this is obviously, it's going to have these 6's go on forever. So you can say 4 and 2/3. So you see what the answer is, right? You see what the answer is. And as I said, for integrals where we can calculate by hand, right, we don't need to do the technique that we are going to learn now. But anyway, let's learn about these numerical methods. Now, those of you who are vicious about learning the real stuff, I have a challenge for you. Program this in. All right, this is what you should do over the weekend now and make the code. Make the code that will do the midpoint rule, trapezoid rule, and Simpsons rule and ask for input how many rectangles, plug in the function. Maybe you will be able to code that in. I believe that was one of the assignments for, if you take this class at NGIT, they have a MATLAB component. You know how we have a lab for this class? We use Mathematica and we use the problems to solve. Well, in their MATLAB, they actually ask you to write the code that will use the formulas we learned today to integrate. And that's one of your assignments. So, you want to be competitive too with those students? Go ahead and create the code for this in whatever your language of choice is. So let's go with the 3 methods. Midpoint. Well, you know what the concept of the midpoint is, the point in the middle, right? So if you have your A, you have your B, this one is A plus B over 2. It's the average of the two values. So what's happening now with my square root example? 1, 2, 3, 4. I just drew it bigger. You see, when you go back to a previous case, I am going to enlarge this. Observe that when you when you do the blue lines, you are counting the area below and you are not counting the area above the line, which means you are undershooting the actual area, and all of this error piles up, and your answer is, right, was 4.1, but the true answer was 4 2/3. So, right, that's where that difference from 1/10 to 2/3, that's that difference, which is error. And that's exactly because we did not account for this area where I put the x's. Now, the red area will take everything from the red line all the way down to x-axis, and that overshoots, obviously, by the amount which is all the way to 5,1, and that's, again, area, the red stuff. Stop flying around. So this would be the error, right? Now let's see if we can do better than that. So say I have this situation, and now instead of using any of the endpoints, I go to the midpoint, I extend the line, and wherever it hits the function, that's where I draw a horizontal line. What did you achieve? Well, you achieved, there is error here and error here, but you see how they don't cancel each other out, but for a good part, they actually balance themselves out. What you overshoot on one side, you undershoot on the other, and even though they don't cancel perfectly, they somewhat cancel. So if I'm computing the function at the midpoint times the delta x, I should get far better result than if I did what I did before, one of the endpoints. So I'm going to do now that thing for all of these. So where am I computing my functions at? At 1.5, 2.5, and 3.5. That's where I'm computing my functions. So what's the formula? If I find the formula for this function using the midpoint, I will have to find the function computed at 1.5 times delta x plus function computed at 2.5 times delta x plus function computed at 3.5 times delta x. I'm looking for area of rectangles. It's length times width. So the height of the rectangle is f of x computed at a value, and the width is delta x. Still 1, right? So delta x is the width of each one of these. So this is equal to square root of 1.5 times 1 plus square root of 2.5 plus square root of 3.5. Now we are going to use calculator for these. And as I said before, you want the challenge? Go figure out how to program this. Because this is what your jobs will be, to program the robots that make things.
Will there be extra credit?
Extra credit. There will be 0 extra credit because I have very high opinion of you. I give treats to my dog when dog does something right. I have higher opinion of you, so no treats, sorry. Yes?
But will there be extra credit?
No.
What if I draw a really, really nice path?
Well, we are past that. There was one-time offer which expired.
Yeah, I draw nice dogs. I draw snakes.
Oh my God. Enough with the extra credit. There will be no extra credit in life. What I get is 4.183. Well, that's a little bit better.
get that. I get that.
Get 4.67.
Yeah, 4.67.
Oh, I missed the plus sign. There we go. There's a plus here. 4.6767. Nice. And the actual answer is this. Pretty damn good, right? Nice. So how do we deal with midpoint? You go into the interval and you find where the middle is in between the 2 points and you compute at those values. Now if we are to come up with a formula, area computed with the midpoint rule is delta x, and then we have f x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus f of x2 plus x3 over 2 plus dot 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 how many of those you have. Now, one thing and that's the formula for midpoint. One thing that will never change is that this dx is always b minus a divided by n. So you know where your a and b are in the limits of the integral. So that's the midpoint. When you get a problem and I say I want 6 rectangles, you just break the division. Let's do 1. We can. There's nothing else to. So compute the integral from, I don't know, 2 to 5 of x squared minus 2 dx with n equals 6. There you go. Yeah, midpoint. That's I know we can all graph this function, but it really doesn't matter how it looks like. You can put whatever. It goes from 2 to 3 to 4 to 5 and then in between. So these are the rectangles that are necessary. And then when we do the midpoint will actually cut all of these in half. Now, we don't actually need all of this stuff because we can say delta x is 5 minus 2 divided by 6, which is 1/2. So we know that delta x is equal to 1/2. And that's the number you keep adding right? So what do I have? Area computed with midpoint is delta x, which is 1/2, and then function computed at 2.5 plus function computed at oh no, sorry, not 2.5. This is halfway in between, so 225. And then plus half on each one until you run out. So plus half, that's 275, plus half, 325, plus half, 375, oops, plus half, 425, and plus half, 475. So area using the midpoint is 1/2 times, and now function is x squared minus 2. So you go and you compute 225 squared, 2.25 squared minus 2. How do we define section like this? Is it hard or annoying? Uh-huh. I probably pushed something wrong. But yeah, I have to change that. So I'll fix it. So my calculation with half is 32.9375. And I have two knotted confirms. Now we can actually solve this problem right? So exact, which is the integral from 3 to 6, 3 to 5. That's what I said, please pay attention. 2 to 5 of x squared minus 2 Oh, I didn't do minus 2. No, I did minus 2. I did it. That's x cubed over 3 minus 2x computed from 2 to 5. That's 125 over 3 minus 10 minus 8/3 plus 4, which is 125. So that's 117 over 3 minus 6. So times 18, right? Times 3 is 18. That works out to be 99 over, is that 33 answer? So look at the midpoint approximation. We did middle school math, right? Addition and multiplication of values, and we got rounded 33, right? So it's pretty sweet, right? How this works. It's a lot of calculations. Now this is something you program the computer to do over 10,000 rectangles. Computer is going to spit it out in a second. Yes.
In the same chapter in Calc 1, when we did summarizing sums, didn't they show us this?
They showed you the left and the right, which is what I did in the front, not the midpoint.
Oh, they did.
They showed the midpoint as well? Nice. So now, yeah, but we have 2 more in this section. So this is the first one out of 3. So now we're doing the next one, which is called Trapezoid Rule. So the Trapezoid Rule, I'll have to check, might be there.
I don't think it was too heavily covered up in this.
Yeah, could be. So for the Trapezoid Rule, here's your 1, 2, 3, 4. What we are going to do is, instead of having this curved line, we are going to connect top points with a straight line segment, creating a trapezoid. Trapezoid has 2 parallel sides, right? A pair of parallel sides and a pair of non-parallel sides. So that's called a trapezoid. Now, this is your x1 and x2. This length here is f of x2. This length here is f of x1. And this length here is delta x. Now, if you remember anything about the trapezoid, I'll put it now sideways to look like this. So this is the same trapezoid as earlier. You know that you have a base 1, base 2, and the height, and the area of the trapezoid is the average b1 plus b2 times the height. That's the area. Now, if you look at our formula, the sides, which are the bases here, are the function calculations, and the height is delta x. So the area of the single trapezoid here, right, is going to be f of x0 plus f of x1 divided by 2. Right, that's the average for those, and then times delta x, which is the height. You look at it sideways, obviously, if you flip that on the side. So that's the area of the first one, right? Will x be, this is x0, x1, x2, and x3. The second one would be the average of f of x1 plus f of x2 divided by 2 times delta x. Now you see that all of the points in the middle are recycled twice, and the points at the ends are only used once. So x0 is used only once to calculate the area of the first rectangle, but x1 was involved in creating the first and the second calculation. So all of that put together, it leads to a formula for trapezoid. So area used the trapezoid is delta x divided by 2. We see delta x divided by 2 in each one of these. And then f of x0 plus 2f of x1 plus 2f of x2 plus 2f of x3 plus the all 2's except the last one, f of xn, is single. In our case, what's single? This one, x3 at 4. So this over here is the trapezoid formula. And we can use this on our previous example. So I'm just going to draw again the square root function. 1, 2, 3, 4. How's the stream? I hope it's working. Well, one thing says stream is working, the other one says it's not, so yeah, he's gonna be very happy that this made a stream, okay? Anyway. Shout out to Chris.
Maybe he was 18 of those 19 views.
Yeah. So all we need to understand, that's x0, that's x1, that's x2, that's x3, and we plug them into the formula. Very quick, very easy. Delta x, so compute delta x over 2. We know that that's going to be 4 minus 1 over 3. That's, again, 3 over 3, which is 1. So 1/2 times, so square root of 1 plus 2 square roots of 2 plus 2 square roots of 3 plus a single square root of 4. So the first and the last have to be single, and every single one in the middle is times 2. That's 1/2 times 1 plus, oh, this needs to be squiggly, 2.8 plus, what is this? We have 1.7, so 3.4 plus 2. All together is 2, 5, 7, 8, 9.2 divided by 2, which is 4.6 in my book. What was the exact answer? 4 and 666, which means 4.2 thirds. 4 and 2 thirds. So again, pretty damn close, right? Now remember, this one approximates a little bit different. You have straight segments that are close to the curvature. Now obviously this method is not very good for something that curves fast, but that's okay. So that's the trapezoid rule. We have one more. Simpsons rule.
Just go back up to the one column here again. Right? How come it's delta x over 2 equals 4 minus 1 over 3?
Yeah.
What's the first one?
4 minus 1
Right.
over 1, 2, 3 rectangles. That's n.
No. But it's
Number of rectangles.
It should be be delta x over 2. It should be delta x.
Or just delta x, yes. That's disgusting, delta x. The last one is the Simpsons Rule. And this one will approximate through quadratics. Now, there's cubic splines later on for a higher order approximation that's provided in graduate school. So there's more, obviously. There's always more. It's math. So we stop with a quadratic approximation, and I will then put all of these approximations into a context, so hopefully they make more sense. So for Simpsons Rule, we are picking 3 points. Now it's very important, guys, to actually have even number. Let me write that in blood over here. Even number of divisions. So n equals 2k. Even number, like 2 rectangles or 4 rectangles or 8 rectangles or 16 rectangles, can't have odd number. You see I have 4, so we pick 3 points and we shoot parabola through those. Then I pick 3 points and I shoot parabola through those. And we go until we reach all of those. So we have again x0, x1, x2, x3, x4. So what's the formula? Again, you can derive this if you're interested. So derivation of this formula would be an honors Calculus 1 honors question for the exam or something. Area using Simpson's method is going to be delta x divided by 3. And now the pattern is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So it has to start with single f of x0 plus, and then it switches to 4 x1s plus 2 f of x2 plus 4 f of x3 plus 2 f of x4 plus dot 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 2 f of x n minus 2 plus 4 f of x n minus 1 plus single f of x n, which is the last one, and then close. So the pattern over here inside is 1, 4, 2, 4, 2, 4, and then 2, 4, 1. You have to end up with 2, 4, 1. Delta x is still good old b minus a over n. N is the number of rectangles, number of divisions.
So that pattern is applied to any application of the Simpsons Rule, or is that?
Yes, and well, that's the formula for it, so yes.
So
And
1,
delta
4,
x
2,
is still
4, 2, 1.
Yeah, so it has to be 1, 4, 2, 4, 1. But if you have multiple terms in the middle, it's going to be alternating 4, 2, 4, 2, 4, 2, 4, 2, 4, 2 until you run out of them.
Right.
But it has to end 2, 4, 1. We have to start 1, 4, 2, and as a mirror end to 2, 4, 1. Yes?
I'm just confused on what the shape is. Like, you drew.
Parabolas.
Um,
Parabolas like this, but you just have a little piece of it, right, that fits the function.
Are they independent or is just one? They're independent.
They overlap.
They're independent.
Yeah. So now let's take a look at our square root problem. Now this is going to be a little bit annoying to compute with this, but you got to do it, right? I'm computing the same problem even though it's not convenient to use this method here. Observe that I need even a number of rectangles, and I don't have that, right? I have odd numbers, 1, 2, 3. So the previous divisions will not work. I have to come up with new divisions in red. So in order to have 4 rectangles, you cut something in half and then in half. So the actual values that I'm computing at are here, and then 3/4 and the 1/4 here. So it's the red ones that and the endpoints. So I have x0, x1, x2, x3, and x4, 5 points. How many rectangles? 1, 2, 3, 4. Cool. I have 4, right? We are not using this part here. Maybe I shouldn't put x there. I'm using the integral 1 to 4 from whatever the hell the function, f root x dx, and I'm looking for 4 2/3.
Why did you draw the first line so close to this number 2?
Because that's the line that it's x1, and x1 is 1.75, and x2 is 2.5, and this is 3.25, and obviously the last one is 4. So they're all 70.75 off. Because, as I said, if I use the old division for rectangles, which is 1, 2, 3, right? 1, 2, 3, 4, I only get 3 rectangles. But Simpsons rule doesn't work for 3 rectangles. You have to have 4 or 6 or 8. So we're going to go to 4, but now the numbers don't match, to be nice, air quotes, right? So what have I done? 4 minus 1 is 3, and then 4 rectangles, 3/4. So you see that each delta x is 3/4. From 1 to 175 is 3/4. From 175 to 25 is 3/4. 25 to 225 is 3/4. And 325 to 4 is 3/4. You can do 6 rectangles. Yeah, but it's 2 more calculations. Right? You have to balance the laziness with, that's a factor as well. Right? Which is usually directly proportional to how much work you want to do. To put that in the mathematical form for you to understand better. So my delta x here is 4 minus 1 divided by, I want 4 rectangles, which is 3/4. So now what do I have? Area using the Simpsons rule is 3/4 divided by 3. And now what do I have? Function computed at the first value, which is 1, plus 4 times, don't forget the pattern, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So 4 times function computed at 1.75, plus 2 times function computed at something, 2.5, plus 4 times function computed at 325, plus just the good old function computed at 4. So those are all square roots. 3 and 3 will cancel, so it just leaves 1/4 here. And then I have a square root of 1 plus 4 times square root of 175. Get the calculators, plus 2 square root of 2.5. It's 4 times square root of 325 plus the square root of 4. And that will approximately be 1/4. And what do I get? I get 1. So 4 times. I'll keep 2 decimal places. 18.66 divided by 4. The exact value without rounding or anything is this, which is again pretty damn close to our 666. Repeating. Wow, time flies when you're having fun. 1 minute left. And then another 15 after that. All right, so those are the three formulas we have. And now I just want to put all of those in perspective. Yes? What happened? On the exam? Yeah.
So we gotta learn.
There's nothing to learn here. Yeah, I know. Imagine this disgusting addition that you have to perform. Oh, by the way, yeah, NGIT and Rutgers Calc2 students are cranking this without the calculator on the exam to 6 rectangles.
Why?
Huh?
How do they find the square root of 1.75?
You have to memorize it, right?
Well, you know, it's like square root of 2 is 141, square root of 3 is 173, square root of 5 is 223, right? You just know them. That's
They we just never got to use it.
what can I say? I mean, you just know those things. That's normal.
I want to know those.
Yeah, you sit one day, you open up, you take a calculator, you write everything down, learn like first 100 square roots down to like a second decimal. That's good enough. First 100 numbers, right? All right. You know already some. Like, what's the square root of 49? See, you know already some of them. It's 7.00, 2 decimal precision, right?
That's wrong, right?
All right. Yeah, square root of 9, 3.00. There's no question there. All right, guys. So what do we have? Now let's put all of this in perspective because unfortunately I don't have time for the next section, so we're pushing it back. Well, courtesy of snow. Yeah, it's disgusting, but what can I do? So we have left rule, right rule, and mid rule. All of which are horizontal line approximation. We call that constant approximation because all of them create that flat linear line on top that is horizontal line. So all of these are constant approximation. Then you have the next level, which is trapezoid rule. That's linear approximation. And then you have your Simpsons rule, which is quadratic. There is another one called cubic splines, which is the cubic approximation, and so on. You don't need to go any higher than that. You can go actually with anything you want. So, you know, looking at these, let's call them 1, 2, and 3, because those are the 3 separate levels. So, number 1, you have a function like this, it will take, right, have that, or that, or that. But all three lines are horizontal lines. For trapezoid rule, we learned that if you have a function, let's curve it like that. For trapezoid, it draws a straight line through, creating a trapezoid. But see, this line over here is y equal mx plus b, which is linear line. It's slanted. And then the third one is quadratic approximation, where you have 1, 2, 3 points, and you fit the best parabola possible through those 3 points. So that one is ax squared plus bx plus c, quadratic approximation. Now, you don't actually see that as you write the formulas and stuff, but that's how it works. And then there are, as I said, higher orders later on. So for this numerical section, the probably most challenging part, which shouldn't be, as I'm going to explain that one more time, is to figure out what are all the values at which you are computing your function, right? You will have to memorize patterns, right? So midpoint has no pattern. The pattern for trapezoid is 1, 2, 2, 2, 2, 2, 2, 2, 2, 1, right? And then for Simpsons Rule, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. 2 end. Has to end that way. Now, you having even number of divisions of rectangles ensures that it ends in 2, 4, 1. All right, now, this is also taught in Calc 1, but they might have escaped you, so I'm just going to real quick talk about it. When we talk about divisions, so let's say you have an integral that goes from, I don't know, 3 to 17. That's a bad number. So 3 to 8 is awesome. Of some kind of integral over here, dx. And you want n equals to 6. You don't actually have to draw a picture if you understand how divisions work. You know that you have to start at 3, and you know you have to end at 8, and you have to have 6 divisions in there. So by computing delta x, which is 8 minus 3 over 6, you are going to get 5 over 6. So your calculations will be happening at every 5 over 6. So your x0 is clearly 3. That's where the world begins. Then the next value, x1, is 3 and 5/6. Then the next value is again 5/6 away, which is actually 10 over 6. And 10 over 6 is now 4. And there are 4 left over. Now, yeah, you can do that and cancel it down to 2/3, but don't, because you still need to add 5/6 again. So the next value, x3, is this value plus another 5 over 6, which is 9 over 6, which is again over 6. So that's going to jump into 5 now. And we are adding, so it was 9. 9 minus 6 is 3, so 3 over 6. That's a half. So x to the x4 is this value here plus another 5 over 6, that's 8 over 6. Which jumps now to 6 over here. And 8, so that's 2 over 6, right? And then the next one, you're adding 5 over 6, that's x5. You add 5, that's a 7. which is again 1 extra. So you get, but see, you don't jump a number now, right? No, you do jump a number because it's 7. So 7 and 1 over 6. And x to the 6 is obviously 8 because you added another. And it has to fall into the last number if you did calculations right. Because 8 minus 3 is this, and over 6, that guarantees. So you will be computing whether it's Simpsons Rule or Trapezoid Rule. You will just go 1, 2, 2, 2, 2, 2, 1 if it's trapezoid, or 1, 4, 2, 4, 2, 4. 1, 4, 2, 4, 2, 4, 1. There we go. I skipped one when and you plug them all in, so it would be delta x over 3. Now, it was very interesting. One student said, do we have to remember these formulas? And I said, hell yes, because that's your Calc 2, okay. The rest of this section is adding and subtracting numbers from elementary computation course, like pre-middle school, okay? And one student noticed something very interesting. I never seen that as a student. I didn't care. I just learned the formula. You see how midpoint going into trapezoid rule, going into this one, the delta x is delta x over 1, delta x over 2, delta x over 3. Like you learn this one first, and this one you learn second, and this one so it's which kind of, I don't know. Why is that? Why was that so important? But I see students forget that delta x is divided by 3 for Simpson. Delta x is divided by 2 for trapezoid, and delta x is divided by 1 for midpoint. See? It's like, all right, fine, right? Over here, you have the averages between x values. On the next one, you have the pattern on the right, 1, 2, 2, 2, 1, and then 1, 4, 2, 4, 2, 4, 2, 4, 1 for Simpsons. Plug values in and try not to make this too complicated. You will have your calculators, at least the basic ones, right? So you can compute these numbers if you are not sure how to compute without a calculator. And this will be one question on the exam, possibly one question final. But the real challenge here and real money maker here is writing that code, learning how to figure out, and even if you're not a computer science major, doesn't matter, right? You learn your own some kind of engineering somewhere. You learn MATLAB, Numerical, Java, I don't know, whatever, Python. I don't care what you do. Just try and write a code for one of these or all three. Have the software ask you to plug in the function, plug in the number of rectangles, plug in the limits, and then just spit out the answer of 4.17 or something like that, right? You plug in those parameters. Guys, this calculator here integrates that way. Makes 10,000 divisions and runs through this algorithm and integrates it. This calculator doesn't solve for x3 halves over 3 halves and plugs limits. It doesn't do, right? This calculator immediately grinds through 10,000 of these and gives you, the precision. They only have to make sure, because this displays 12 decimals or whatever, right? They just need to make sure that they compute the 12 decimal precision. How many of these rectangles they need to use? 5,000, 10,000, 100,000? And I remember the one that I mentioned at NGIT, one of those labs was to write a computer program that will actually have 10,000 of these calculations. So your step is delta x, and you just figure out what is the function that you plug in, because, right, and just make a loop for 10,000. Spits out all of the numbers like this and adds them up. So it's not a big deal. You shouldn't have like 10 lines of code or so to figure it out. So figure it out. It's an interesting exercise. All right, so that's it for today. Next time we're talking about improper integrals. Very important section. And if we have time, we'll do the differential equations. I hope you downloaded the lab. Let me just say bye to stream. By stream?